In this lesson, we're going to learn about sigma notation. Sigma is a Greek letter that's used to represent a summation. A summation is basically when you take a bunch of terms and you add them together. So we're adding together the terms of a sequence. So you see the symbol above with the sigma in it. There's a number below the sigma, n equals 3, and then there's a number above, 7. And then there's a function that follows the sigma. What sigma does is it adds up all the function values, starting with f of 3, and then it adds to it f of 4, plus f of 5, plus f of 6, plus f of 7. So it counts all the way from 3 to 7 and takes and adds those terms together. The right side of the equation is called its expanded form. The letter n represents what we call the index of summation. And those values are consecutive whole numbers. In the case above, 3, 4, 5, 6, and 7. The initial value is 3, and the final value is 7. So let's see how that works in a particular example. In example 1, we're only going to write the expanded form of each summation. We're not actually going to evaluate any expressions other than to write it in expanded form. So in example 1a, we have the summation as k goes from 2 to 5 of g of k. That is equal to g of 2 plus g of 3 plus g of 4 plus g of 5. We start at 2 and we end at 5, and we simply add those terms together. In b, we have a more specific function. The summation as n goes from 5 to 9 of n squared. So this is equal to 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared in expanded form. All right, your turn to try C on your own. Pause the video while you do this. You should have gotten f of 0 plus f of 1 plus f of 2 plus f of 3. This illustrates that occasionally we'll use 0 as a number in the summation, as it is an input number. All right, let's try D on your own. Try that and pause the video. Did you get 1/7 plus 1/8 plus 1/9? Great, you're getting the hang of this. All right, now let's take a look at an example where we're actually evaluating the summation. So in example 2a, we have the summation as k goes from 1 to 4 of 3k plus 1. For these, I'm going to suggest that you make a table of values and put your input k in the first column, and then the output 3k plus 1 in the second column. So our k's start at 1 and then count up to 4. And so now we're just going to fill in the other side of the table. If k is 1, then the value of 3 times k plus 1 is 3 times 1 plus 1, which is 4. 3 times 2 plus 1 is 7. 3 times 3 plus 1 is 10. And 3 times 4 plus 1 is 13. What you'll notice about this sequence of numbers, 4, 7, 10, and 13, is that they form an arithmetic sequence. What we're about to do with them, which is add them together, is an arithmetic series, which is just a sequence of terms that has been added together. If we add 4 plus 7, that's 11, plus 10 is 21, plus 13 is 34. So 34 is the value of this summation. Let's try B. So in B, we have the summation as n goes from 0 of 1/2 raised to the n power. So we can make a table of values for this one as well. And you may find that on some of these you want the table of values, and on some of them you may not need it. So we're going to start with n equals 0, count up to 4. And so if n is 0, 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared is 1/4. 1/2 to the 3rd is 1/8. And 1/2 raised to the 4th power is 1/16. So now we're just going to simply add these together. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. And if you like, you can just use your calculator to add these terms together. So 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and that's 31/16. You'll have your calculator for this entire unit. All right, a couple for you to try. Try A below. The summation is A goes from 3 to 5 of A squared, and pause the video while you do this. Did you get 50? Good job. All right, now try B. The summation as K goes from 2 to 5 of K squared plus K. For this one, you should have gotten a final answer of 68. All right, now we're going to move on to taking a series rather, and working it backwards to find the series in sigma notation. So some strategies. You can draw a 2-column table with headers K and F of K, and write the index in the K column starting at 1, and then write the terms in the F of K column. And then we're just going to work with the pattern here to see if we can find a rule that will give us the function that turns the K's into F of K's. So we have K here, and we have F of K, which you can also call A sub K if you want. You could also use N instead of K for the input variable. It's really up to you. All right, so we have a first term, and it looks like we have a total of 6 terms here. We're probably not going to need to list all of them to get what the pattern is, but we start with a first term of 18, and then I want to think about how I'm getting from term to term here. So it looks like from 18 to -6 to +2, we are multiplying by -1/3. So 18 times -1/3 gives us the -6. 18 times -1/3 times another -1/3 gives us +2, and so on. I'm not going to list all of the terms here. Let's go back and fill in some of the assumed exponents. For instance, the -1/3 in the second row has an exponent of 1, and in the first row, that 18 is multiplied by -1/3 raised to the 0 power. Let's make some observations about the values of K and our exponents. It looks like when K is 1, the exponent is 0, K is 2, the exponent is 1, K is 3, the exponent is 2. So that means that in each case, our A sub K, or our F of K, is 18 times -1/3 raised to the 1 less than the value of K. So in sigma notation, this summation is the sum as K goes from 1 to 6 for 6 terms of 18 times -1/3 raised to the K minus 1. All right, let's check out a different sequence. 2 plus 5 plus 8 plus 14 plus, and then the ellipsis to indicate that there are some terms missing. And then we just have a final term of 128. So for this one, it is not quite as obvious how many terms are actually in this sequence. So let's use n for our variable this time, just because, and a sub n in the right-hand column. So if n is 1, that means our a sub n, our term, is 2. If n is 2, now we need to look at that pattern. So 2 to 5 to 8 to 11 to 14, it looks like we are adding 3 each time. So the second term is 2 plus 3. The third term is 2 plus 3 plus another 3, which means 3 times 2. And the fourth term would be 2 plus 3 times 3. 2 plus 3 times 3 is 2 plus 9 is 11 is the fourth term. Let's go back and fill in some of the assumed values. In the second row, it looks like that 3 was being multiplied by 1. And then in the first row, the 2 Since it has nothing added to it, we could say it's plus 3 times 0. That gives us an idea about what the pattern is here. What you'll notice about those multipliers of the 3 is that they're all 1 less than the term number. So what that means is our a sub n is 2 plus 3 times 1 less than the term number. Now you could also use the general formula for the nth term of an arithmetic sequence if you want. It's going to give us that same exact pattern, or you can just develop the pattern with a table. So let's simplify our a sub n just a little bit. That's 2 plus 3n minus 3, and combining like terms, that's 3n minus 1. So this sigma is, it occurs to me that we still don't know how many terms are in this sequence, in this series rather. So let's go ahead and take that last term, 128, and let's put it in our formula where a sub n, the term is. So if 128 is equal to the general formula for the term 3n minus 1, then 129 is 3n, and dividing by 3, that's going to give us 43. So it looks like there are 43 terms in this sequence. So when we write the summation, n will go from 1 to 43, and then the formula to generate the terms is 3n minus 1. It's important that you use parentheses around it whenever there is addition or subtraction in the terms, just to avoid confusion about what part is inside the summation and what part is outside. A quick note about the ellipsis. We had the ellipsis in the middle of the series in the last example, and that indicates that there were some terms missing. We weren't going to write every single term of that sequence, but we write the end to show where the sequence ends. A series in expanded form that has an ellipsis at the end actually indicates that that series never ends, or it has an infinite number of terms. So let's take a look at example 3, in which we have a series 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus, and then you can think of that ellipsis as saying etc. So I'm going to write a table of values here. We have our n's, 1, 2, 3, 4 will probably give us enough to generate a pattern. And then our a sub n's. A sub n is 1/2, that's our first term. And to generate each term, it looks like we are multiplying by 1/2, because 1/2 times 1/2 is 1/4, times 1/2 is 1/8, times 1/2 is 1/16, etc. So the second term is 1/2 times 1/2, or 1/2 squared. The third term is 1/2 cubed, and the fourth term is 1/2 raised to the 4th power. There's an understood to the 1st power in that first row of the table. And now let's look at those exponents and compare them to the term numbers. It turns out they are exactly the same as the term numbers. So it looks like our a sub n is just 1/2 raised to the n power. So in sigma notation, this is the summation as n goes from 1 to, and at the top of the summation we'll put infinity to indicate that this series has no end. And then our general term is 1/2 raised to the n power. Quick fun fact, even though that particular series has an infinite number of terms, its sum is finite. That is to say, its sum is not infinity, even though you're adding terms indefinitely. And that's because of the size of the terms. So to illustrate this, I'm going to draw a square, and we're going to shade some fraction drawings here. Let's assume that this square represents 1 unit. So what I'm adding is 1/2 of the square, shade that in, plus 1/4 of the square, plus 1/8 of the square, plus 1/16 of the square, and you kind of see where this is going. if this process continues indefinitely, we'd eventually be moving toward having that entire square filled in. So what this illustrates is that the sum 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus etc. actually equals a finite sum of 1. All right, more examples of writing in sigma notation. In example 4, we're going to write the series 9 plus 16 plus 25 plus 36 plus 49 plus 64 in sigma notation. And you might recognize this immediately, that those numbers are perfect squares. Well, 9 is the square of 3, so for this series, it may make sense for us to start our summation at 3. I think in general we want to start at 1, but if it's very convenient for you to start at 3, by all means use that initial index to make your generating the pattern a little bit easier. So when n is 3, 4, 5, 6, our values are 9, 16, 25, 36, which are 3 squared, 4 squared, 5 squared, and 6 squared. So it looks like our pattern is that the terms are just n squared. If we write it in sigma notation, this is the sum as n goes from 1 to, and it looks like there are, actually we're not starting at 1, right? We're starting at 3, because 3 squared is 9. And where do we end? We end at 64, which is 8 squared. So it looks like the sum as n goes from 3 to 8 of n squared. Let's take a look at B. In B, this particular sequence is not in itself a geometric or an arithmetic sequence. But if we look at denominators, so for instance, our first term is 1, and if I write it as a fraction, it's 1 over 1. Second term is 1 over 4. Third term is 1 over 7. Fourth term is 1 over 10. And the denominators themselves, 1, 4, 7, 10, are forming an arithmetic sequence. So we can work with the denominators as a pattern here, and the denominator 4 comes from adding 3 to 1. The denominator 7 comes from 1 plus 3 times 2, and 10 comes from 1 plus 3 times 3. Let's put in some hidden numbers here, like 3 times 1 for just plain 3. And then for our initial term, this could be 1 over 1 plus 3 times 0. So those multipliers of 3 are all 1 less than the term number. So it looks like our general term, a sub n, is equal to 1 over 1 plus 3 times n minus 1, which is 1 over 1 plus 3n minus 3, or 1 over 3n minus 2. So written in sigma notation, this is the sum as n goes from 1 to, and it looks like there's no end to this series, so 1 to infinity, of the general term 1 over 3n minus 2. All right, check out this last one. 2 times 3 is 6, times 3 is 18, times 3 is 54. We have a times 3 type of a sequence. That's geometric. So if we generate this table of values, first term is 2, second term is 2 times 3, third term is 2 times 3 squared, fourth term is 2 times 3 cubed. Let's go back and put on our assumed values for those exponents. So we really have 3 to the power of 1, and if there's no 3, that means that we're multiplying by 3 to the 0, which is 1. Those exponents are 1 less than the term number. So a sub n is 2 times 3 to the n minus 1. Now we still have to figure out where this series ends, because this one doesn't go on indefinitely, but it certainly does go on for a while, since the nth term, or the last term of this sequence, is 9,565,938. So let's take that number and let's put it in the formula for a sub n, which generates the terms, replacing a sub n with that number. We have an exponential expression there. What we're going to need to do is to isolate the exponential expression so that we can use logarithms to solve this equation. In order to do that, we'll have to divide by 2 first. I'll put my calculator over here where we can see that. So we're taking 9,565,938 and dividing it by 2. And that gives us 4,782,969 equals 3 raised to the n minus 1. So now if we use logarithms, the log base 3 of that number, 4,782,969, is equal to n minus 1. And so adding 1, n is 1 plus the log base 3 of 4,782,969. And let's calculate that value. I'm just going to use the answer feature to do this. Log base 3 of that previous answer that was stored in the calculator, so I don't have to retype all those digits. And we get 15. If you miskey something with a logarithmic form, you'll probably know that there's some error in there because you won't get a whole number, and we're looking for the term number, which needs to be a whole number, not a fractional value. So our sigma for this is the sum as n goes from 1 to 15 of, and the term formula is 2 times 3 to the n minus 1. All right, some ones for you to try on your own. 1 minus a half plus 1/3 minus a quarter plus 1/5 minus 1/6 plus etc. So try this one on your own and pause the video. All right, this one was just a bit challenging. You really have to think of this one split up in terms of just looking at its numerator and denominator. So the numerators are 1, -1, 1, and -1. That's really a multiplying sequence. We're just multiplying by -1 each time to get the next term. So we can really use the form of a geometric sequence for that, which is the general term is the first term times the common ratio raised to 1 less than the term number. And so our numerators are just -1 raised to the n minus 1. Now the denominators, I made a separate table for those. And for the denominators, it looks like the denominators are exactly the same as the term numbers. So that means the denominators are just n, the same as the term numbers. All right, try B on your own. And hint, this is one where you may not want to start your counter or your index at 1. The solution to this one depends upon your recognizing 8, 27, 64, 125, and 216 as perfect cubes, the cubes of 2, 3, 4, 5, and 6. All right, try C. Hint, this one's an arithmetic series. Pause the video while you try this one. Here's the sigma notation. The sum as n goes from 1 to 20 of 4n minus 2. As a reminder, you need the parentheses around 4n minus 2 if in the general formula has any additions or subtractions. Those need to be included in the parentheses to show that they're part of the summation. This one also required that we take that number 78 and we figure out what number term it is by taking our formula for the term and setting it equal to 78 and solving for n. All right, try this last one, D, on your own, and this one is going to be one of those where the numerator and denominator are two separate sequences. So treat them separately. All right, here's our solution to the last one. The numerator was an arithmetic series with a common difference of 2. So we can use the arithmetic series formula to find it, or we can just generate the pattern based off the table. The denominator was a geometric series or geometric sequence with a common ratio of 2, but this one turns out to just be powers of 2 where the exponent matches the term number. So that's a fairly easy sequence to generate from the pattern, but separating them certainly helps. Well, that's it for this lesson.